Okay, let's put it into practice and show a real demonstration. What we've got here is a web application, and it's dynamically generated from some back-end processes and scripts, which we'll get into as we need to. What we have is a composite resource. This resource has an identifier. Here it's got a URL. And when we generate this resource, we actually see that it contains requests for lots of smaller individual resources. Here, resource 1, resource 2, resource 3, and resource 4. And we see that they they contain a timestamp when they were generated. Here, they were all generated around about exactly the same time, and therefore they have exactly the same time inside their value. We're representing the value of the time through changing the color of the boundary around the resource, just so that we can visually see the effect of the pattern. If we look at the source code for how that resource is generated, we see it's being generated using the XML recursion language, which is a language that comes with NetKernel. It's an XML. It's like X-include on steroid, if you like. And here we see that the resource is just an HTML template containing a title. And here we see there's a sub-request made for resource 1, resource 2, resource 3, and resource 4. So we see the composite generated on our web page contains those values. Let's look at how each individual resource is generated. They're actually generated when the res1 is requested. It actually gets routed through a mapper to a Groovy script that executes to generate that resource. Let's look at that script. The first thing we notice about this script is that the request comes in and we obtain the integer index of the value for this I resource from the request that's come in. Next thing we do is we just do some simple stuff to compute the date and determine a color value from that date value. Then we use Groovy's string templating ability. We just create this little div block. Before we return this representation here at the end of the process as our response, we issue a further sub-request. Here we construct a request to attach golden thread, and we associate with this request some arguments. Here an ID of virtual resource $1 $i, which is the I index value. So here we're associating a specific value dependency that's exactly indexed against the same identity as the resource. We also associate a general resource called virtual resource all. So this resource is common to every resource that's ever generated through this endpoint. And then finally, we do a simple parsing of the integer value and decide if it's odd or even. We then set a dependency on that resource to the odd or the even set of virtual dependencies. We issue that request, and by doing that we associate this representation we're about to return with these three sets of possible resources. Okay, returning to the demo. If I re-request this resource, we notice that nothing's changed in the application. I can request it as many times as I want and it'll come straight out of cache because the system's monitoring all the dependencies for us. Nothing's changed, and we didn't explicitly expire these resources, so they get cached each time. Okay, let's look at the golden threads. Let's try expiring golden thread 1. What I just did was I issued a request to a resource here, and one of its side effects was to cut the virtual resource 1 golden thread. It obviously took the value from the request and associated with that single resource. If I look at the composite resource now, see that resource 1 has now expired. Its time is now 11:36:45 and the original is 11:32:42. Let's cut all the golden threads. So that's expiring virtual resource all. We now see that all of my resources are aligned again. They were all regenerated when I re-requested the composite because it was determined that the cache value is no longer valid because the golden thread was expired. We see they've all got exactly the same value. Let's cut all the odd golden threads. Here we've cut resource odd. looking at the composite resource, we now see that resource 1 has been updated, resource 3 is updated, resource 2 and resource 4 are still the same values. Okay, that's the demo. Just to conclude what the architectural implications of this pattern are. It's very common in a resource-oriented system to be able to differentiate not just horizontal boundaries in our application, but also virtual channels through the application. So we can quite easily differentiate read channels in which requesters and endpoints and so on create resources and representations and composite values from sub-resources, and eventually these percolate up, and very naturally the caching boundary tends to reside close to the top near the requester. And because most applications are read more than write, then we get lots and lots of accumulated values for reuse in the cache. When we compute these values, the endpoints that generate these things can, as necessary, associate virtual dependencies if we want to. So we hear the representation from this endpoint is associated with some virtual dependency. As long as that virtual dependency is valid, and as long as all of this state is valid, then the requester will continue to hit the cache and get representation from there. If at some point in the future some state comes into the system down one of our write channels, and that state gets persisted perhaps out to an external database or other persistence mechanism, then before we commit that state change to the external mechanism, we can explicitly expire the golden thread, the virtual dependency 2. And therefore, this write channel, without any knowledge of who or what depends upon this representation or this set of golden thread dependencies, can influence the cache on this side of the channel. So this representation in the cache becomes instantaneously and atomically expired, and any subsequent request for that resource will end up having to go and compute all of the state change again and associate with the new virtual dependency. Effectively what we then have is, between our two sides of our architecture, we have read channels, we have write channels, and there's no code dependency between these two areas of our application. The only thing that they have in common is a shared algorithm for how they compute the identity of this golden thread. That's the golden thread pattern.